All right. So after discussing some basic services with OS, I'm going to continue discussion on internal view. Some of the slide we have discussed earlier in our previous lectures. That's the reason I told you guys earlier. You don't have all the videos. Reason some of the videos have been, or some of the topics have been covered in other areas. So I don't do videos chapter by chapter, but depends on the topics. All right, with that, let me get started with this topic, the internal view of OS. I've shared this slide number of times, hierarchical model of an OS. Yeah, so we as a user at the top, we communicate with the system or operating system using interface, user interface, as what we have just discussed, either using command utilities or GUI. That's what we do, all right, on our side. And then at the OS side, of course, there are different layers, which is known as a kernel space. Either you use file or you use system commands, or you need API, or you need application. It depends what are you looking for, what kind of services are you, or jobs that are you interested. So when you look at such as file services, the commands in file services, either command line interface or GUI, will communicate accordingly to network services or process management services or resource allocation. For example, you need to use hard disk, or you need to use primary memory, or you need to use IO, or you need to use printers, for example, or screen, or you might need to use virtual memory. It depends, it depends what services or what jobs are you planning to execute. And some of these services might require IO, which means require IO device drivers in order to communicate with the hardware. Or if you require network, then network definitely require network services and so on. So this is just an example of how user interface using appropriate interfaces to communicate with the system, and for the system to communicate with the rest of the resources in order to get your job done. So this is what we call internal view. In the previous slide, we viewed at external view. So how user make use of all the services available at the operating system. That's what we call user view. But now we are moving into internal view. We're going to look into how the system, handles all your requests, handles all your job in getting completed or in getting done. So with that, we will look at some primary kernel function. Some of these topics, again, like what I said, we have discussed previously, but let me run through it again. The one important tool in your Windows or in your Linux or even Unix is what we call the file manager. File manager, or sometimes we call Windows Explorer or File Explorer, translates logical file requests into specific physical IO requests, right? So when you give a command, for example, file open, which you are giving it through GUI, but that command is actually being executed in a command line at kernel level in order to look for the file exactly from the hard disk, from the storage, secondary storage, before it is being loaded into the main memory and it is being shown on your screen. So there are a lot of steps or activities involved for your with your request, with your logical request. Also, IO control system, IOCS, perform resource allocation and device management. Like what you have seen earlier in the chart, in the diagram, when you make a request, it goes all the way to IO drivers, and it involves certain hardware to be accessed, Also, it requires memory management, determines if it is possible to load program and data into memory? And if so, which memory, for example, RAM or VM or any other memories, registers, okay, or temporary memory, which memory, plus the location of the memory, the detailed part of the memory. Remember, we discussed all that in chapter 1 or chapter 2, how the little man computer works, how your main memory works. Main memory consists of memory address and memory location. So you must think up to that level, very low level. And also, we did discuss about scheduling software 2 weeks ago in detail, how the scheduling software, which is a software as part of the OS, allocate time for program to execute, either under the environment of single user or multiple user. All right, and then beside the kernel function, in order to get your job or request done, we also need to understand this program, bootstrapping, which is a program, which is a software, as all of you know, it is in a ROM. It is in a ROM. Execution begins with bootstrap loader. The program name, sometimes we do call it as a BIOS, basic input output system, where you can press certain function key in order to view that in a different operating system. So this bootstrap programming is a program stored in ROM, read-only memory, for your system to get startup or boot up. That's why they call it bootstrapping. And it is always in the ROM, in the ROM. Loads this program, BIOS or bootstrap programming, once you power on your laptop or desktop or your PC or your devices, will be loaded into RAM. And then transfer the control to OS. So without BIOS, you are unable to start up your devices. So transfer control to starting location of OS. So OS will take over the control from BIOS, and then OS will work as usual, like what we discussed earlier, to get your request done or job done. So make sure you are aware of this bootstrap programming. Not much of detail here, but I hope you understand what is bootstrap, the function of bootstrap, the location of bootstrap, and why this program is so important. There is a one chart in your next slide, simply to differentiate the cold and warm boot up. Warm boot up does not retest the system. Cold boot up, which is a detail, require the retest. So normally we have an option. The normal option is warm boot up instead of cold boot up. Example, the bootstrap program or loader is in the ROM. When computer is started, execution begins with bootstrap loader, permanently stored in ROM, number 1. Then look at number 2. Bootstrap loader locates operating system kernel program, usually at a fixed disk location. Normally it is in a RAM. Of course, RAM is temporary memory. Definitely the OS is in your hard disk. So from hard disk, it will be loaded into RAM. From the hard disk, from your SSD or hard disk, the bootstrap loader locates the OS kernel program and loads into the RAM. Number 3. Number 4, transfer control to the starting point of the operating system program with the JMP instruction, jump instruction, meaning pass the control from the hard disk into the RAM. So this is an example of how the bootstrap program is being executed or being launched, and then transfer the control from the bootstrap program to the kernel, which is in the OS. Okay, I hope all of you understand this process. 1, 2, 3, 4. Remember this just in case they ask you this in the exam, especially in part 2, where they will ask you short structured question to explain how bootstrap program is being executed. So if that is the case, if that is the question, you should be able to explain 1, 2, 3, 4. If you can draw this diagram, will be good. Otherwise, at least explain 1, 2, 3, 4. Depends on the mark given to you for that particular question. Okay, next we're going to discuss about processes, OS related processes. Yeah, what we call basic unit of work in the OS. We have discussed this number of times, even under the topic scheduling. But again, we will look into different perspective, yeah, different aspect of it in this chapter. So process, we're going to look at basic unit of work in the OS. A program together with all the resources that are associated and what need to be executed. So we look at all the program within the OS that need to be associated, that need to be executed, associated with the resources, meaning by looking at what are the resources required. Also, we will look at a file or listing of file. Also, we will be looking at program, especially we can also look at a list of program that will be executed to complete your process. Continue on the discussion. We will look at independent and cooperating processes. Also, we will look at PID. PID, process ID, which you can always look at your task manager. PID, which is a unique identifier for each process. You can see that in your task manager. Task manager will show you all the processes that are running currently. Yeah, active, passive, with the IDs. Also, we will discuss some processes related to how you create the process or how you start the process, such as forking, spawning, cloning a new process, parent and child process. Okay, it's same like how your main program runs subroutines or some sub-programs, or we call it child processes or child programs in order to complete your job. Also, we will discuss about some related registers like what we have discussed earlier, MAR, MBR, IR, PC, and so on. Some of the registers that you always must remember. Also, we have discussed about interruption, very detailed discussion in 2 weeks ago. So please, yeah, so all that will be discussed up to a certain extent so that we can discuss processes involved in OS. All right. So please stop me if you have any question or if you need any further clarification. Otherwise, I'm going to continue with the next slide, which is on PCB, process control block. Where you can see the PCB, I have told you many times, PCB is available in Task Manager. You can always open your Task Manager and look at PCB. What is PCB? A block of data for each process in the system. When you have a process running, for example, you launch a program, Word, you launch a program, Excel, you launch your system, calculator, for example, utility program, or you launch Paint, for example, any utility programs or any apps that you launch within your Windows or Linux or Unix, all these will be recorded into PCB, will be recorded into your Task Manager. That's why Task Manager is a very detailed program, keep track of everything. So it is a block of data for each process in the system, contains all relevant information about the process. Typical process block is on the right. What you have, if you open your PCB or your Task Manager, and then you look at your process, it has process ID, very unique process ID. Pointer to parent process. If it is a child process, it will refer to parent process. Pointer area to child processes. Process state, the status of the process, running or on hold, pause, or stop. Program counter, register, save area, memory pointers, priority information. Accounting information is more like a user information, who is using it, whether it is under network or single users, multi-sharing, multitasking. So it has a lot of information about that one particular process. That is what we call PCB block. I have seen questions, questions asking you in the exam, what is PCB block? So make sure you know the information or the answers are in this slide. So you can quickly draw and show some of the details, not necessarily all, to answer what is PCB. Next, process state. Yeah, process state, basically one of the information from here, process state. Can you see this? Process state. What is process state? Like what I have explained earlier, 3 primary process operating state, either ready state, running state, or block state. We have covered all this in the diploma level, where you used to draw the diagram, process state diagram, and then you used to show whether that process, that activity is in a ready state, running state, or block state, or suspend state. Remember? So we're going to discuss that again. Dispatching, like what we have covered in previous lectures, move from ready state to running state. That is what we call dispatch. Dispatch means executing. It's like in our common life, we have a dispatch runners to bring things from one location to the other location. So it's the same in the system. From a ready state to running state, we call dispatching. Wake up, move from block state to ready state. Block meaning suspended. From a suspended state to a ready state. Wake up. Then we have timeout. Timeout means from running state to ready state. So remember these 3 states. You don't have to remember really about what is dispatching, wake up, and timeout, but you must remember this ready state, running state, and block state. And then the transition, ready state to running state to block state to running state, also running state to ready state. Those are the transition that you need to know. Process completion, how you can complete a process or terminate a process. You can kill the process, terminate or stop the process, or completely interrupt and destroy the process. Yeah, you can do all that. And of course, you know what are the commands. Either you use GUI or you use command line to do that. Additional state, like what I mentioned earlier, we have suspend, and also sometimes we do swap. For example, when you press alternate tab, actually you are swapping the control from one process to the other process. So that is swap. Then resumption is like resume again, move from suspended state to ready state. So these are the so-called state or process states that you need to know. We will see this in a diagram. Of course, they won't ask you a question about all this theoretically. They will ask you to draw a diagram like this. Yeah. In the exam, they will ask you to draw what we call process state diagram, PSD. Example, from a new process which has been created, yeah, and then the process one, it is created, it will turn into a ready state. From the ready state, it can get dispatched, meaning move from the ready state to running. Remember, dispatching. And then from the running state, it can also get blocked. Yeah, blocked into a block or suspended. Sometimes we call it block or suspended due to some reason. IO not available, CPU busy, memory out of space. So can get blocked. It's like hold, and then wake up again to ready, and then to running. So while you're running, if you're running out of the CPU time, especially under multitasking, multi-user, there will be a timeout. Then you got to wait for your turn. Once everything done, completed, exit, terminated. All right. So you can pick up any example if you want to include example for this discussion. All right. For example, you launch an Excel file from a new, you launch the Excel application, and then you open up a new file, you work on it, running, you work on it, you save. Let's say no interruption, you exit. But if there is some interruption, let's say you want to print, the printer is not ready, then you have to wait, block, so-called block or suspend. Or while you want to save the file, hard disk is full of space, no space, then you have to do something to the hard disk before you can save, if it allows. Sometimes it doesn't allow. Whatever you type will be gone if it is not safe. It depends on the situation. So all that can happen. So you can pick up any example, and then you discuss along this process state diagram. But the common process state diagram is something like this, similar to this. So remember this, over here you can see all the states: ready, running, and block, the main states. And what are the transactions taking place in between the states? Any questions, guys? Any questions? Stop me, unmute, and speak. Otherwise, drop in the chat box. I'll talk to you later. Threats. Let's continue our discussion with threats. Before, let me see what's the time now. Okay. Before we take a short break later. Threats is basically a mini process that can be run independent of other parts of the process. It's a mini process. It's not a main process, sub-process. It's based on event-driven program. Sometimes this mini process requires resources allocated to its parent process, including primary storage, files, or I/O devices. Depends on what you are planning to do. Each thread adds its own context. Advantage of process or thread families over multiple independent processes. Reduce OS overhead for resource allocation and process management. Substantially less information than normal PCB. So it has less information than normal process control block. This is basically like a child process. When you want to do a main process, the main process can be broken down into child processes, and the child processes can run independently. For example, maybe this child process requires just one small portion of the resources. So it can run while the main process is running or doing other job. If you put all the processes or all the activities together in the main process, then the main process will get delayed, because the main process will make sure all the resources are available. But that is not possible under the multi-user or multi-sharing environment, because the resources always will be used by many users. So sometimes you have to wait for the resources. I hope you understand. When I refer to resources, you need CPU resources, you need memory resources, hard disk resources, you need display screen resources. But all these resources under the multi-user environment, especially the server, will not allocate all the resources just for you. The servers are for everyone, every user. That's why in our previous lectures, remember we discussed, the CPU will give slice of time for every user to use the resources. And we discussed that in using many different examples under scheduling, under prioritization. So you must understand all that concept very well. And moving on in down the road, in next couple of slides, we will be applying some of the concept that we discussed previously 1 or 2 weeks ago. So this mini process, or we call it thread, is an event-driven program. For example, when you need to do that particular event, you run this, otherwise you don't. For example, it can be a backup, small backup program, or small burning a disk drive, burning a disk, for example, CD or DVD, or it can be a small antivirus scanning program. It runs independently, when you execute, or it is a small calculation portion which doesn't require main resources, but certain parts, just small parts of the I/O resources. What you can see in the next slide, before we stop for a break, is loading and executing a process. Yeah, let me run through this, then we can take a short break. Process management. So there is a request program. So when there's a request program, it will definitely look for a buffer space. If buffer space is available, then only the request program will be handled by the OS. And it will check the memory, whether it can be loaded into the RAM. Because if RAM is full, busy with other processors, normally you have to wait. Your request will be put on hold. Otherwise, it allocates the space, load the program, retrieve the directory required from the hard disk where the program is, and then if there's any I/O required, read directory from the disk, retrieve the program, read the program into the main memory, and then set process status ready, and then continuous process start and so on. Just imagine, to run a program, you need to do all this checking. You have to make sure the buffer space is allocated, load the program, retrieve from the directory, retrieve the program itself, load into the RAM, make sure the status is ready before you can run. So this is basically the same as this diagram. Same as this diagram, process state diagram, but into more detail. So what you see is the top part is important. Process management, file services, memory management, dispatcher, I/O services. These are the 5 main services or areas or factors that need to be considered when you need to load and execute a process. This is just one process. Just imagine in your OS, you may run 5 to 6 processes or 10 or 15. It depends on the environment, how busy. Some people like to open 20, 30 tabs. You might run many processes. Some run one at a time. Some run 2. So this is how each process will get loaded and executed in the system. Okay, guys, with that, let me take a short break. Okay, let me